everyone. This is Dr. Anna, your geology professor in historical geology. Today we are going to talk about plate tectonics. I will refer back a whole lot for physical geology, where we did learn the structure and plate tectonics somewhat too. This time we're going into much more detail, and we're going to talk about a lot of the sedimentary basins and what kind of sediment forms in what kind of plate tectonic environment. So if you think that it's going to be just like it was in the physical geology, it's not really true, because as I say, we're going to go one step beyond that. So we're going to talk more about the different sedimentary basins, how do they form, and what kind of sediment will accumulate in them. So let's start with the different kind of plate tectonic setting. I could say that the three major, if you look at the movement, the three major environment is the extensional, compressional, there's an L missing right there, and the transform. Extensional, when you have the plates moving apart from each other. The compressional is when they're moving toward each other. And the third one is the transform, when they actually slide next to each other. Wait, how is the camera? Like that, slide next to each other. So the first two will have vertical movement. When it's extensional, one block is moving down. When it's compressional, one is moving up. But when it's transformed, they are just sliding next to each other horizontally. So there is no vertical but only horizontal movement. So let's start with the extensional setting and talk a little bit about the structure which happens in that plate tectonic setting. So when we are in the extension, remember the plates are moving away from each other, they are pulling apart, and most of the time these forces are going to result in normal faults. Normal faults. Remember the normal faults? When you have normal faults, and remember a little bit of the fault geometry. This here is the fault line. That's the fault plane. And the block which is moving is the hanging wall. Remember hanging. And the one which is not moving is what we call footwall. And to define which one is what, all you have to do is just do an imaginary horizontal line along with the, along the fault line. And if you look below the horizontal plane, you can see that there is an acute and there is an obtuse angle. The acute angle side is always the hanging wall. So that's the wall, that's the block which is moving. And the obtuse angle will be always the one which is not moving, which what we call the footwall. Remember, I just told you. Now, if you have extension, that means that the forces are acting in opposite direction. And the result is going to be always relative lengthening, because they are going apart. So you're going to have relative lengthening. And the way you're able to see the relative lengthening, that you will have layers, parts of layers missing along the fault line. Like here is this brown layer, you see right here, and the other side. And there is this little area where that brown layer actually is missing. And that is the length of the relative lengthening in this situation. So if you see missing layer, even without being able to tell which one is footwall, which one is hanging wall, you know that that's an extensional plate tectonic setting. And what kind of plate boundary would you have these? Where you have extension. Yeah, you're right. It's a divergent plate boundary. Divergent plate boundary. So just remember that. And this just shows you a typical normal fault, which is characteristic in extensional plate tectonic setting. And you can see the fault line itself shown with yellow. And if you put the horizontal plane right there, you see this is the acute angle. So this here is going to be the hanging wall. And you pick a layer, like let's say this little white layer, you can see on the hanging wall side, this layer moved down. So it's a normal fault. And you can also see that there is this missing. The white layer is missing in this little area. So it's a typical normal fault. A lot of the times when you have extension, you not only will see one normal fault, but a series of normal faults. And very many times, actually, they are facing each other. And that is when we call the type of fault series like Graben faults. This is a Graben fault. It's very, very characteristic at divergent plate boundaries. So remember, when they face each other normal faults, we call it Graben fault, Graben fault. And I have on this slide very typical Graben fault, actually, which is happening in Sierra Nevada. This is the Owen Valley Graben right here. You can see it's two facing each other normal fault. It's a typical Graben fault. So this is very characteristic in the western US. And this slide was made in Death Valley, this picture I should say. And you can see a typical, yes, I hope you all said Graben fault, actually it says it right there. You have the two facing each other normal fault. This is the fault line for one fault, and that's the other. And if you put the horizontal plane on, if you put the horizontal plane on, like let's say up here, so it doesn't bother, this is the acute angle, so that's the hanging fall for this fault, and this is the footwall here. And if you pick a layer, let's say this one right here, see, on the hanging wall it went down, so it's a typical normal fault. Now if you look at this side and you put the horizontal plane, this is the acute angle and that's the obtuse. So this is the hanging wall and this is the foot wall. And if you pick that layer again, let's see this one right here, you can see that it went down. So it's a typical Graben fault. Two facing each other normal fault, Graben fault. They're always of the result of extensional force, like the forces going opposite each other, and it's relative lengthening. This is where you see the missing layer right there. So this is a typical Graben fault, remember. Okay, when you are in the compressional stress environment, which is the convergent plate boundary, what's going to happen if you put the horizontal plane, you see this is the acute angle, so that's the hanging wall, and this is the foot wall. See what happens when it's compression, you got the forcing going toward each other, the forces going toward each other like it shows right there, and it will result in a relative shortening, like the forces are acting opposite against each other basically, and the result for that is compression. So basically you will see relative shortening here, and the amount of shortening is that if you look at this brown layer, it's actually repeated on the hanging wall. So basically you got the amount of relative shortening right here. Wherever on both black you got the brown layer that repeats, and that is the amount of shortening which has happened here. So it's very easy to see that it's a reverse fault, because when you have reverse fault you will have the layers, the same layer repeating on top of each other, because that's when one block is moving over the other one, and that is what we call relative shortening. It's compressional stress, and it's going to be on convergent plate boundaries. And this slide shows very typical, this picture shows a typical reverse fault. That's the fault line, and without even looking at which one is the hanging wall, which one is the foot wall, you can see that this layer is being repeated. So it's a typical reverse fault, compression. These are the forces. One is going this way, the other one is going up the other way. So right there, they are being pushed together and you will see a relative shortening. There is another one. When the angle of the fault is really, really low, less than 45 degrees, we actually call it thrust fault. And on thrust faults, the shortening can be much bigger than just normal reverse fault, which means high angle reverse fault. When the angle is really low, the movement can be really a whole lot. So we call it thrust fault. Thrust fault is a special type of reverse fault where the angle of the fault is less than 45 degrees. Okay, the the third kind of setting, plate tectonic setting, we should say the transform setting. And this is when the plates sliding next to each other, as you can see right here. So one plate is going this way, the other one is going this way. And we have two kinds, the so-called left and right lateral strike slip. Left and right lateral strike slip faults. It says right here, strike slip faults. If it's left lateral, you can stand on one block and see that the other one is moving to the left. So you're standing here, moving to the left. But if you're standing here and looking which way this is going, still going to the left. Now, when you have right lateral strike slip fault, then this block is moving that way and this one is this way. And if you're standing here, watching the other one, you can see it's going to the right. So that's a right lateral strike slip fault. Left and right lateral strike slip fault. The San Andreas is a typical right lateral strike slip fault. This picture actually shows a typical strike slip fault. You can see how the original straight layers actually become messed up by this fault line. The fault line is right here. And to tell if it's left or right, you just follow one of these trees and you can see that it actually moved to the left. So it's a typical left lateral strike slip fault. So this block is going this way. This block is going this way. So it's a typical, if you're standing here, watching which way the other plate is going, you can see it's going to the left. So it's a left lateral strike slip fault. Okay, so this is about the faults. And now we're going to just go through really quick the inside layers of the earth so you know what makes plate tectonic possible. Remember, we have the solid inner core, iron and nickel solid. We have the liquid outer core, it's also iron and nickel. And then you got the mantle, and in the mantle we got the asthenosphere. Remember, the mantle is solid, but the asthenosphere is a quasi-liquid layer on which the plates actually can move. Above the asthenosphere, we got the lithosphere plate. And remember, the lithosphere is not one rigid plate. It broken up into a couple of big lithosphere plates. And some of those lithosphere plates will have continent on them. And those are continental lithosphere plates. And some of them will just have ocean. So it's the oceanic lithosphere plates. Remember, the lithosphere is the uppermost part of the mantle and the crust. Uppermost mantle and the crust. So this slide shows you the major lithosphere plates, like the Pacific plate right here, the Eurasian plate, the African plate, Eurasian the North American plate, the Australian plate, and so on. Here is the Juan de Fuca, Cocos plate, South American plate, and so on. So these are the big plates. And at their boundary, we see the three kind of plate, meeting plate, like divergent, convergent, and transform. This also just shows the movement along this plate boundary. So here is the South American plate, and American, yeah. I was afraid that I don't see it so well, so I just wanted to make sure. And here is the mid-oceanic ridge in the Atlantic Ocean, and that's the African plate right here. So it's kind of interesting to see. Okay, so why would the lithosphere plates move? And the reason for them is that we have the so-called convection currents in the mantle. Some areas in the mantle are more hot than others, and wherever it's cooler, it's kind of pulling down. And the reason for that is, remember, when you have a convergent plate boundary, the oceanic plate is able to go down because it's as dense as the mantle, whereas the continental plate can never go down because it's lighter than the mantle. So this plate, along the cold part of the current, the plates are pulling down, and that kind of pulls the plates apart around the mid-oceanic ridges. And it's also more hot in these areas. So we have the upwelling part of the current here, and this is the downwelling part of the convection current. So it's convection current which causes the plate tectonics to work. It's very similar to when you cook. Actually, if you have a heat source right here, this area is hotter, so it's less dense, it's moving up, and this area is cooler, so it's more dense, so it's moving down. So this is the convection current. Convection current in the mantle causes the plate tectonics. If you play the slideshow, this you can see how the higher temperature is moving up and the cooler temperature is moving down, because it's more dense, so it's moving down. This is lighter, so it's moving up. And this is how we have these three type of plate boundaries: the divergent, convergent, and transform plate boundaries. So we're gonna start with the divergent plate boundary. In the formation of the divergent plate boundary, we have two major phases. One is the continental rift, and the other one is the oceanic drift. When you have a continental rift, basically, at the very beginning, a graben is forming because the plates are being pulled apart because of the magma is pushing up. So it wants to come up, and that pushes the plate apart. So the first sign will be you're going to have earthquake, you're going to have a lot of volcanoes, and they are actually, because they are coming from the mantle, if you remember, it's going to be mafic, mostly basalt. And as I just said, the very typical graben. Very many times when the continent starts to break up, it starts as a so-called triple junction. It's like when you bake bread and you put the dough in the oven, and then it makes a crust on it, but underneath the dough is still rising, and it breaks up the crust, and usually the breakup happens along three arms. These arms are 120 degrees away from each other, just like that, and we call this triple junction. So normally on the continent, when you have a new ocean starting, most often it's going to start along three arms, and interestingly, out of the three arms, only two will make it into ocean, and usually a third one will become failed on. And I will show you in a minute an example, but first just let's go with the typical graben first. So here we have typical graben faults. I already showed you this picture, so you kind of remember the Sierra Nevada and the Inyo Valley. And here you can see more of it. This is Salt Lake right here, Salt Lake. And then you can see that the mountains around there are typical graben faults also. So this whole area is actually being pulled apart, just like on this slide, as you can see. This is because of the extension. These graben faults usually going hand in hand, so you'll have a series of grabens forming usually. And this is a very good example. These are the Canyonland grabens. If you've ever been in Utah, you know, just above Arizona and Utah, and if you go to Monument Valley, and if you go north on that road from Monument Valley toward Moab, Canyonland is right there. So when you fly over Canyonland, you will be able to see actually these typical graben faults here. This whole area is nothing but graben faults, which is really amazing because these areas are absolutely gorgeous. If you ever have the chance to go and look at it. So here is this typical graben fault, and it is the result of the magma wanting to come up and pushing the plates apart just like that. So this is typical. One of these in these taps is the Lake Baikal graben fault. It's a very, very cool example of typical continental rift. The lake is very, very deep. Usually the graben faults are always filled up with fresh water, and as long as they don't reach to the ocean, they do stay fresh water. So if you look at the seismic profile of Lake Baikal, you clearly can see the graben faults. So actually it's a series of normal faults, just like here. And the other very good example is the Dead Sea. Actually, the Dead Sea is a typical rift zone also, where the two plates are pulling apart right here. And this is what I already kind of mentioned just as a beginning, that very many times they start as a triple junction. After that first Graben fault, actually the triple junction becomes pretty obvious. And the best example for this is Eastern Africa. And this here is the Red Sea, this is the Gulf of Aden, and that's the East African Rift Basins. So you can see the typical triple junction right here. And there is another triple junction, the Azori triple junction right here. It's very close to the Atlantic Ocean, the Atlantic Mid-Oceanic Rift actually. And the most beautiful and most typical is the Red Sea, the Gulf of Aden, and the East African Rift Basins. And with this triple junction, it's a typical continental rift. You can see the 120-degree. All the red triangles are typical basalt volcanoes. Here is the Lake Tanganyika, the Mount Kilimanjaro, typical situation. So the Red Sea and the Gulf of Aden already have oceanic crust. The regular seawater already moved in. So most likely the East African basins are going to be the failed arm. Failed arm. Because as I mentioned, remember only two will make it into ocean. The third one is going to be the failed arm. So the East African Rift Basins, that's the name for it, is a typical failed arm. On the test, I will have matching. You have to put the name of different, I will put divergent plate boundary or typical triple junction. You have to put it toward the Gulf of Aden and Red Sea. And the failed arm, you have to say the East African Rift Basin. So you have to match them together. And of course with the other plate boundaries also. I'm going to stop right now. This is section 1, segment 1. And I'm going to continue in the next one. I'll see you.